Okay, welcome to CO527 Advanced Database Systems course. Today's topic is on distributed databases. So let's look at the overview of today's session. So first we'll discuss distributed database concepts, and then we also discuss a little bit about the advantages of those. Then we also discuss things related to the database, distributed database concepts, data fragmentation, how data is actually distributed in different nodes, and data replication having multiple copies, and then their allocation techniques. Then we will also discuss how concurrency control is handled, like how multiple users can access the data items in a distributed database, and how we are going to recover in case of failure. Then we'll move on to distributed transactions. So how you can actually have transaction processing in distributed database environment. So under this we will talk about two protocols, two-phase commit protocol, as well as the extension to a two-phase commit protocol is known as three-phase commit protocol. Then we move on to discuss how query a process in a distributed database environment. And finally, we will discuss the different types of distributed database systems available. So that's the overview of today's session. Okay, so let's start from the basic concepts. So what is distributed database? So if you go with the definition, a distributed database is a collection of multiple logically related databases distributed over a computer network, and a distributed database management system as a software system that manages a distributed database while making the distribution transparent to the user. So as you can see, here there are two parts. One thing is you have a collection of logically related database, and it is distributed in different parts and in different places, and then you have to have a distributed database management systems to handle this, manage this distributed database. So but when the user works with the systems, the user will not feel that the data coming from different databases. So he or she will see it as a one single unit. So which means distributed database is actually a combined resource of two technologies, that is the databases as well as the network. So let's look at what happens in the recent years. In recently, distributed database technology is actually used to collect vast amount of data, and this is known as big data technologies. Then once you have collected the data, so you can actually apply the other technologies like data mining and machine learning algorithms to extract the knowledge from this data. Okay, yes, let's look at the advantages of distributed database system. Let's look at the advantages of distributed database systems. The first one actually the transparency. Now for example, when you look at the distributed databases, as you can see in the figure, it is actually distributed in several multiple nodes, right? And we have a communication network to connect all these together. But user will not know these details. So he feels that data is coming from a single place. So this is called distribution transparency, or sometimes we call data organization transparency. Next, let's look at an example. Now in this particular case, you will see three tables. We have employee, project, and works on tables, and they are actually fragmented horizontally, which means it's actually part of the records are kept in different places. Now, for example, in Chicago headquarters, you will see all the records, all the tuples are recorded for all the tables. But if you go to branch San Francisco, for example, it contains the details on employees in San Francisco and Los Angeles, and projects on San Francisco, as well as works on relations San Francisco. Likewise, if you look at the New York, you will see the employee details related to New York, and it contains all the details about the projects, as well as those employees works for the projects on New York employees, right? So this is an example with how the data is actually fragmented. With sometimes you will see multiple copies of the same. We call replication. Then distribution and network transparency. So you don't, for example, users, they don't have to worry about the operational database of the network, right? And then, for example, if you look at the locations, right? So users can actually show from any location without affecting its work. So this is called location transparency. And then there's another thing called naming transparency, which means like you can access any named object like files, relations from any location. And this is known as distribution and network transparency. Then replication transparency. So replication means, as I told you, like you can have multiple copies of the same. So it stores the copies of the data multiple sites, like the example we have seen. So this is done to minimize the access time, because when you actually apply queries to a particular location, so if the data available in the same location, and then it takes a less access time. Then fragmentation transparency. It allows to fragment relation horizontally. You will see that some of the tuples that you can put it in. In previous example, we have seen horizontal fragmentation, and this is also can be in vertical fragmentation. That means some of the columns of the relation you can keep it a one node, and the rest in the other node, right? And this is called vertical fragmentation. Okay. Other advantages. So the first one, improved ease and flexibility of application development. So when it comes to developing applications and maintaining applications in different geographically distributed sites is facilitated. And then increase reliability and availability. Now reliability means system in live time. That is running efficiently most of the time, right? And then availability means that the system is continuously available. Now, if you look at the centralized system, and if it is fails, the whole system cannot be accessed. Now, in this particular case, we have several nodes and data is replicated, which means failure of one node affects the overall system. Next, improved performance. Improved performance, which means data actually keep close to where it is needed most. That means we sometimes call data localization. And because of this, it reduces the management access. The time significantly reduced, which will improve the performance of the system. And the next one is easy expansion using scalability. That means now if you want, you can add more data, and you can increase by adding more data into the database size. so that adding more nodes, it's easier compared to you will handle the centralized system. So this scalability actually comes into two parts. Horizontal scalability, as we discussed earlier. So that means you can add new nodes anytime changing the configuration, or vertical scalability, which means like you are going to improve the capacity of the individual nodes, which means like you increase the data, the size of the data or the capacity of the system, as well as improve the performance. Okay, so data fragmentation, again, we can talk about multiple ways. So in this part, actually, we are going to look at this, how the data is actually put into different parts, and this is called fragmentation. And again, for this we have two ways, so horizontal fragmentation and vertical fragmentation. Okay, let's start with the horizontal fragmentation. So this is also known as Shadi. So what happens there? It will actually select a set of tuple which satisfy particular condition, put into a subset of relations. Now, for example, we discuss our employee database. So in that particular case, in employee relation, we can meet some condition. For example, let's say we want to get those who works for department number 5. So all these tuples belongs to department number 5, that you can actually create a subset of it, and then this is called horizontal fragment of employee relation. So which means when it comes to selections, like you did earlier, you can connect several conditions if you want using NOO, and also like derived horizontal fragmentations are there. So that means it's partitioning of primary relations to other secondary relations, and then you relate these each other with foreign keys. Then you can also have vertical fragmentation. So in that particular case, you are going to select a subset of the columns. So that means a particular vertical fragment contain a selected set of columns. So there's no selection condition, but then you have to have any key attribute distributed among these fragments, so that you can actually combine them together. Now, for example, if you take employee relation, vertical fragmentation would mean you are going to keep name, birthday, sex, and then address. So keeping only that part will be a one vertical fragmentation. So as I told you earlier, so when you are fragmenting, you have to include this primary key, so that actually you can connect all these different vertical fragments. Okay, so let's look at replication, right? So replication means in this particular case, database distributed, and then you are going to have copies. So if you are going to keep the whole data set, entire data set, so this is also known as fully replicated distributed database. So that means you are going to keep all the data in a particular site or a node. And then you can have a partial replication. That means a selected part you are going to replicate. So how we are going to distribute this is we call data allocation, and this is only relevant for partial replication, right? So basically the idea is the selected portion is distributed to the database site. Okay, let's look at the example. In this particular example, what you see is our company database, and this is fragmented, and This is horizontally fragmented, choosing only those who works for department number 5. So in this particular case, what you see here is the relation fragment that we call site 2, and it corresponds to department number 5. And the next one will show you those correspond to department number 4, right? So I hope now you have got the idea. So in this part, we are going to discuss about the concurrency control and recovery. Now, when it comes to distributed database environment, there are numerous problems arises. Now, for example, you have to deal with multiple copies of the data items. Because the concurrency control actually responsible for maintaining the consistency about these copies, right? So if there's something fail happens, the recovery management systems to it should recover all copies and maintain the consistency of the recovery. So compared to centralized database system, so this is additional problem we may face when we have distributed databases. And the next one is a failure of individual sites. So sometimes these different nodes or the sites may fail, but it should not affect this failure. And recovery system should be able to recover, right, before they are available to use. Then communication link failures. So sometimes all these sites are connected through the network. The network failure may create what we call the network partition. So sometimes the data site will be working, but network is actually failed. Then distributed commit. Now when you are committing a transaction, so that the transaction will be fragmented and then it may executed in different sites. So that means you have to have some ways of handling this commit for the transaction commit, right? So we will discuss later on 2-phase and 3-phase commits. So this needs 2 or 3-phase commit approach for transactions to come, because you have to make sure that for example, when it comes to committing, so all sites should be in agreement to commit to make the global commit. And then since you are working with the several sites, right? So there could be like distributed deadlocks. So the deadlock may occur in several sites, right? So 2 or more sites may get in a involved in a deadlock. So that means you have to handle this in a distributed manner. Okay. So let's look at how distributed database systems actually handles this concurrency control and recoveries. So first we are going to look at this concurrency control based on what we call the distributed copy of data item, right? So sometimes this is also known as the distinguished copy. So for example, in primary site technique, a single site is designated as a primary site. So in the figure you will see there are 5 sites, and then we will designate the site 5 as the primary sites. So whenever transaction executes, so this will be works for as the coordinator site for all the data items. So all the logs are kept at that particular site, and all requests for locking, unlocking are also sent into that particular site. So when it comes to transaction management, concurrency control and commit are managing this designated site. Now, for example, in 2-phase locking, we will go into details. So this site actually manage the locking and also releasing the data items, right? So the key idea is if all transactions follow this two-phase policy in all the sites, then serializability is guaranteed. Remember we discussed this idea. So although transaction happening in the live fashion, but it executed such a way that it works in the serial fashion. So how do you do this? We have checked this serializability. So serializability is guaranteed in case all transaction it follows two-phase policy at all sites. Transaction management advantages, extensions to the centralized two-phase locking. So implementation management is simple. So it's actually one designated site, and data items are locked only one site, but they can be accessed at any sites. So those are the advantages. But there are some disadvantages also, because all transaction management actually should go to the primary site, which may overload this site, right? And another disadvantage is, let's say the primary site fails, then entire system is inaccessible. So what we can do is to recovery when such activity happens, that you can have a what we call the backup site. Then we have, instead of having a primary site, you can have primary copy technique. So instead of the site, data item partition is designated as a primary copy. So all the locking and actually handle with this primary copy. So the advantages are, so these primary copies could be distributed in various sites. So single site is not overloaded like in previous case. But the disadvantages is like identify this copy is a complex one, right? And you have to maintain a distributed directory in all the sites to handle primary copy technique. Okay, now let's look at the recovery from coordinator failure. And remember we discussed two techniques, having one particular primary site, or going to have primary copies. In both cases, that means the coordinator site or copy may become unavailable. So then we need to select new coordinator. So let's look at the options. Now let's say we have a primary site approach with no backup site. Then what will happen? You have to abort and restart all transaction in all sites, and then you have to select new coordinator, and then you have to initiate the transaction processing. Let's look at the other option. Like let's say you have a primary site with backup site. So in that particular case, you can suspend all active transactions, and then you can designate the backup site as a primary site, and also you can actually identify new backup site. And then primary site receive all transaction management information to resume the processing. So let's say you don't have a primary site as well as no backup sites, or both fails. Then you have to election process among the sites. You have to find out a new coordinator site. So that's how the recovery happens. Okay, let's look at another way of handling concurrency control. So in this particular case, it's based on voting. So there's no primary copy of coordinator. So which means you need to select the locks to the sites which has that particular data item interested to lock. So if the majority sites grant the lock, then the transaction gets a data item, and this locking information is sent to all these sites, right? So there will be a timeout in case there's a long waiting time. To avoid that one, we it specify some timeout period. And if the transaction does not get any vote information, then transaction is bored. Let's look at distributed transaction. So distributed transaction means, so transaction may update to 2 or more systems. I told you like the data is distributed among multiple sites. So the challenges are, how do you handle the machines, the software, network failures, while preserving this transaction integrity? Right. Now for that, each computer runs what we call this transaction manager. So transaction manager actually responsible to keep track of all these sub transactions. And transaction managers communicate with the other transaction managers. So once one transaction manager on one side will connect with the transaction manager in the other side. And transaction manager is one to prepare, commit, and abort calls for the sub transactions. So every sub transaction should agree to commit, right? Changes before the transaction can complete. So first of all, you have to have an agreement. Now for these agreements, these commits what called the consensus. So basically consensus means it agrees on a particular value proposed by at least one process. So let's say coordinator proposed to commit transaction. Now coordinator is the one who's managing it, and then the other sites are known as the participants. And if all the participants agree, then you can commit. That means all the participants then commit it. Let's say participant will not agree, then all participants has to abort. Right? To data be consistent, so everybody should agree. So basically what it means, you have a unanimous agreement to commit it. So let's look at two-phase protocol. So as the two-phase commit protocol means, there's a propose for committing by the coordinator, and the other transaction managers are known as participants. They'll receive it. Then once the coordinator proposes, they have to say whether they are in agreement, yes or no. So in this particular figure, you will see coordinator send the commit for all the participants, and then it will get the acknowledgement saying yes and yes, and finally one participant say no. Right. So now I think you got the idea of the two phases. The goal is to reliably agree to commit or abort a collection of sub-transactions, because this transaction happen in different multiple sites, and transaction managers are in those sites are responsible to handle this. So all processes in the transaction will agree to commit or abort. Now we talk about this earlier as well. It's a unit data item. Either it will actually execute, it's a logical unit, or it will abort. So in two-phase commit protocol, as I told you earlier, like once you have the transaction managers, one of them actually selected as a coordinator, and the rest are known as the participant. Okay, so in this case, it assumes that write-ahead lock. So this means like whether before you perform the actual task, you are going to write in the log. And then it also assumes that there's no failures in the systems. No system dies forever, right? Which means it will come back. And then systems can always communicate with each other. So with those assumptions, we can actually look at what exactly happened. So earlier also we discussed when it comes to transaction, there are different states. So you have a start, you have committed, you have aborted, and then once you have actually prepared. So when the participant enters the prepared state, then it contacts the coordinator to start the commit protocol to commit the entire transactions. So as I told you earlier, like there are two phases. In phase 1 we call voting phase. It actually get the commit agreement from every participant. So the coordinator will send the message commit to all the participants. And if single no, that means we have to abort the transaction. And the second phase we call commit phase. And then once you actually received yes from everyone, and then coordinator will send the results of the vote to every participant. So it could be either commit or vote. Right? So if everything is success, then you send commit operations to all the participants, or else it will actually send a vote message to all the participants. And then once we have this, the participant should acknowledge, saying that okay, I have committed. Right? So the coordinator expect this acknowledgement from every participant. So this is how the two-phase commit protocol works. So now let's look at how to deal with failures. So two-phase commit assumes the fail recovery model. That means any fail system will eventually recover. So, but to make sure that a recovered system cannot change its mind. So that means if let's say one node agreed to commit, then let's say it's crashed, and it should willing and able to commit when it recovers. And each system will use a write ahead log and keep track of where the protocol like start, and also the committing, that means request for the commit, and all these phases are recorded. And also like what are the values to enable commit or vote. So if you look at a little bit of details like how messages are passed between coordinator and participant. So in one side you will see the coordinator, the other side you will see the participant. So participant actually works on transactions, and then they'll wait for message from the coordinator. Coordinator will actually write the prepare to commit to log, and then it will send the commit message. Remember, we talk about write ahead log. So before you perform any operation, so you are going to write in the log and then perform. This is to avoid undo. So you can always go with redoing the operation. So once the coordinator sends the prepare to commit message, the participant receives this, and then when it's ready, then it will write agree to commit or vote in the log. And the coordinator side wait for all participants to the response, right? So the participant at the end say agree to commit or vote to the coordinator. So this is called voting phase. So basically what happens there is it will get the distributed agreement. That means the coordinator asks each participant and then wait for the replies from the participants. So the second phase, as I told earlier, commit phase, if you go into details, coordinator writes commit or vote based on the agreement received from the voting phase. And first of all, it write in the log and then send the commit to the participant. And participant it to wait for the commit abort message, and it will receive the message from the coordinator. And it is commit, then it will participant will first write commit in the log and release all logs, update and the databases. Let's say it will receive a vote, then undo all changes, and finally it send a message to the coordinator. And once the coordinator receives the acknowledge from all the participants, it stops. Right. Okay. Let's look at the failures. Failures in phase 1, that means voting. So what could happen is one failure could be coordinated dies. So that means some participants may have responded and others have no clue, right? So what will happen is coordinate restarts and check the log. Remember, it's a write ahead log. It look at it understand it's a voting in voting was in progress. That means restart the voting phase. Let's say participant dies. Then what will happen? After sending vote to the coordinator, the participant may have died. So if the coordinator receives the vote and wait for other votes and go to phase 2, otherwise wait for the participant to recover and respond. Keep on asking this. Okay, let's look at failures during phase 2. Coordinator dies. So what could happen is some participant may have given the commit or vote instructions. Coordinator restarts, it will check the log and then inform again the older participants chosen the action. Let's say participant dies. Then the participant may have died before or after getting the commit or vote request. So this is in the second phase. So coordinator keeps trying to contact the participant with the request, and participant recovers, checks the log, gets a request from the coordinator. If it is committed a vote, acknowledge the request. Otherwise, process the commit or vote request and finally send back the acknowledgement. Adding a recovery coordinator. Now sometimes, as I told you, like if the coordinator fails, we have to have someone to take over the coordinator. So this could be a participant. Let's say it's detected timeout from the coordinator, then another system can take over. So this is called having a recovery coordinator. So recovery node needs to find where the status of the protocol. Now when, let's say, a coordinator fails, recovery node first of all look at the status of the protocol. So how it actually knows the state, basically it will contact all the participants and to see how they have worked. So if you got the voter results for all the participant, we know phase 1 completed. If everybody is agreed to commit, then send commit, otherwise send a vote. Let's say any participant has not voted, then we know that the phase 1 is not completed, so which means you can restart from the beginning. But let's say participants crashes, then you have to wait for recovery. So let's look at the issues in two-phase protocol. So the biggest problem in two-phase protocol is it's known as a blocking protocol. Now for example, if the coordinator crashes, then participants have no idea whether to commit or vote. So in case if you have a recovery coordinator, it may help. The same thing happened with non-responding participants, because we know that you have to have unanimous agreement. If one of the participants will not respond, then it will block in the protocol. When a participant gets a commit or vote message, does not know if every other participant was informed the result. So that is also another issue. So to overcome this, then the two-phase commit protocol extended into three-phase commit protocol. So same setup, that means you have coordinators and participants, and then add timeouts to each phase, which will result in a vote. And propagate the result of commit or vote to each participant before telling them to act on it. So before they commit, you have like prepare to commit. So this will allow to recover state if any participant dies. So how it happens is it will split the second phase into two parts. So that means commit phase. You have two parts. What you have new is you have pre-commit phase. It has a separate message of prepare. That is prepare for commit. Right? So participant can prepare to commit but cannot do anything that can be undone, and participant reply with the acknowledgement. So the purpose of this phase is to let the participant know the states of the results to vote, so that state can be recovered if anyone dies. Then the other one is commit, right? Same as in the previous two-phase commit protocol. So if the coordinator gets acknowledged for all pre-commit messages, then it will send the commit message. Otherwise, it will abort. So let's look at all the phases together. Phase 1, like in the previous case, we have voting phase. So coordinator starts sending can commit. It's try to find out everyone agrees to commit. If coordinator gets a timeout, remember this time timeout is introduced for all the nodes, and no replies, then abort to all participants. If the participant timeout waiting for the request from the coordinator, again it abort itself. So that means it assumes that the coordinator is crashed. Or else it will continue the second phase, which means we call pre-commit or prepare to commit phase. So it will send the prepare message and expect the acknowledgement from all the participants. Again, the purpose here is let the participant know the decision. If the coordinator timeout, so assume that participant crashed, send abort to all participants. Because this is coordinator cannot count on every participant having received the prepare message. And phase 3 is a finalize or the commit. It will send the commit message to participant and get response. If they are in timeouts, then contact any other participant and move to that state. If coordinator times out, that's okay. So let's look at the recoveries. If the coordinator crashes, then recovery node can query the state from any available participant. So possible state that participant may report in this case is already committed. So that means every other participant may have received the prepare commit. Some participant may have committed, some are not. So in that particular case, the recovery node can send commit message to all the participants. Let's say it's not committed but receive a prepare message. So this means that everybody is agreed to commit. So that means recovery node has to send, coordinator has to send the prepare commit to everyone and wait for their acknowledgement. Let's say it has not yet received the prepare message. That so means participant has not committed. Some may have agreed. So that means you can restart the protocol. Okay. So what are the weaknesses? Even three-phase protocol has weaknesses. So for example, one problem is when network get partitions. I know that all the nodes actually rely on the network. So sometimes networks get partitions. So let's look at an example where let's say one partition node receives a prepare message. So recovery coordinator for A is allows commit. And let's say partition B nodes that did not receive prepare message. So that partition, they have not received the prepare message. So recovery coordinator for B is aborts. Because it's depend on this one. So now you have two recovery coordinates for partition A, partition B. Now either of these actions are not legitimate as a whole, because let's say when the network merges back, system is inconsistent. So you have two different states. So not good when a crash coordinator recovers. it needs to find out someone to go and stay quiet, or otherwise it will mess up the protocol. So which will lead to a inconsistent state. Okay, so let's look at the coordinated recovery problem. Let's say the coordinator send a prepare message to all the participants, and let's say the participant acknowledge this message. And at that time, the coordinator dies before it got all the acknowledgements. So recovery coordinator queries the participant. So continue with the commit, sends prepare, gets acknowledged, and then send commits. At the same time, original code recovers. It realized that it still misses some replies from the prepare, timeout, and decide to send abort. Right? Recovery coordinator tries to commit it, and then the coordinators try to abort this, which will make our database in the consistent state. Okay. So in this part, we are going to discuss query processing in distributed databases. There are different issues when it comes to distributed system. You have to consider additional factors which will further complicate the query processing. First one is what we call the cost of transferring data. That means over the network, right? So because the data could be in one site and other site, you may perform the query and then transfer data in this site, will cost little high. So some optimization is necessary here. Now let's look at an example. Let's say we have employee relation in site 1, and let's say we have a department at site 2. So we have two relations in two sites. So in the first site, let's say we have 10,000 rows, and let's look at the row size is 100 bytes. So the table size will be 10 to the power 6 bytes there. If you take the department at site 2, let's say you have 100 rows and the row size is 35 bytes, then table size will be 3500. Now let's look at the distributed query, right? So let's say for each employee, we want to retrieve employee name and department where the employee works. So that means we have to get, if you look at the relational algebra expression, we have pi f name l name div. This is what we are going to have. But to get this, we want to combine both, join both employee and the department with this join condition, and then you are going to project it. Right. Now let's look at the result. The result of this is you will have 10,000 tuples because you have 10,000 employees. You need then their names and then their department details. So let's see, each tuple is 40 bytes long, right? 40 bytes long. And then let's assume that the query is submitted as site 3. Results is going to send this. The problem is site 3 does not contain any of these relations. That's the problem. So that means some data transfer should happen. Okay, so let's look at some strategies. So in this particular case, we are going to look at 3 strategies. The first one, let's say transfer employee and department to site 3 because we need the result in site 3. You have to transfer both employee and the department. So the total transfer byte is, we talked about earlier, for employee it's 10 to the power 6 plus 3500. You get 1,03,500 bytes. Let's look at another scenario. Let's say you are going to transfer employee to the site 2, and then you perform the join operation and then you send the results there. So we discussed earlier the resource size is 40 bytes. That means we have 10,000 records. So 400,000 bytes will go for that. So the total transfer is you have to transfer the employee table to site 2, which takes 1 million. So altogether you will get 1,400,000 bytes. That's the second. Third one, let's say you are transfer department to site 1, perform the join and then send the results to site 3. So that case, transfer in 1 you have 400,000, and then you are putting what we call the department into site 1, that is 3,500, 400 and 3,500 bytes. Okay. So optimization idea, let's say we take it as a minimum data transfer. We know the preferred approach is strategy 3. Okay. Let's consider another one. For each department, let's say department name and the department manager's name, right? So if you look at the relational algebra operation, we know that you perform the joint operation between employee and the department. The joint condition is manager social security number should be equal to social security number of the employee, and we want to get the first name, last name and department name, right? So results of this query will have 100 tuples, because like every department, if we assume the manager, right, then the results will have 100 tuples. So let's look at the execution strategies. The first one, you can transfer employee and department to the resource side. It means perform site 3. So the total byte transfer byte 1 million plus 3,500. You have 1,03,500 bytes. Second one, you transfer the employee to site 2. Join operations. They are send the results to 3. So that means in this particular case, it's 14 to 100, we have 4,000 bytes. So 4,000 plus 1 million, or 1,000, 1,004,000 bytes. If you do the third strategy, so that means you put the department site 1, it's with join and transfer. So that means 4,000 means 40 into 100, 4,000 plus 3,500, you will get 7,500 bytes. So here also the preferred strategy is 3, if you look at the minimum number. So now let's look at the result site is 2, right? So that means we can transfer employee relation to site 2, execute the query and present result to the user. So the total transfer is 1 million bytes for both queries, Q and Q dash. And the second strategy, transfer department relation 1, execute join in site 1 and send the results back to site 2. That means total transfer is 400,000 plus 3,500 for the first one, because you are going to get 100,000 employees. So the result size is 400,000. So you will get 3,500. Q dash, you will see that it's 4,000 plus 3, that's 7,500 bytes. Okay. So let's look at the semi-join, right? So that means the objective of this semi-joins is to reduce the number of tuples in the relation before it transfers to another side. So example execution, if you look at Q and Q dash, what you could do is project the join attributes in the department site 2 and transfer them to site 1, right? So for Q, it will be 4 into 100, 400 bytes are transferred, and Q dash, it's 9 into 100, 900 bytes. Then join transfer file with the employee relation and site 1 and transfer the required attribute from the resulting file to site 2. So let's say it's a 34 bytes, then it's into 10,000, you get 340,000 bytes. And Q dash will be 39 into 100, 3,900 bytes. Then execute the query by join transfer file with the department present in the site 2. Right? So these optimizations are, possible, and you need to consider the details. Okay, so let's look at the final topic, the types of distributed database systems. So the first one we call homogeneous. That means all the site of database system have identical setup. That means you have same database system software, right? So the figure says same database system software, but the operating system might be different. So you will see site 1 you have Unix, database is Oracle. Site 2 you have Linux and Oracle. Site 4 you have Windows and Oracle, right? And then heterogeneous, you have two types, federated and multi-database. So each site may run different database systems, but the data access managed through the single conceptual schema. So for example, we have site 1 hierarchical with Unix, relational with Linux, site 2, site 3, network DBM is Linux 3, and so on. So then we have multi-database, which means there's no one conceptual global schema. So data access schema is constructed dynamically as the application software. So the issues with the federated types, so different data models, remember it supports with different schemas, relational, object-oriented, hierarchical network, and differences constraints. Each site may have their own data accessing processing constraint. Differences in the query languages, some may use SQL, some may use 8-9 different versions of this, and so on. Okay, so with this one